Good morning. My name is Kina Trowell, and I'm a PhD candidate in the Alternative Fuels Lab at McGill University. And this morning, I'm going to be presenting some of our work on supercritical metal-water reactions for in-situ hydrogen production. Now, our energy system is one that's largely driven by solar energy. We capture some of that energy using PV cells, hydro dams, and wind turbines, but the way that we use most of our solar energy today is actually through photosynthesis. So all the energy we get from biomass, and this includes the food we eat as well as hydrocarbons, is really just transformed solar energy. The problem that we're facing now is that we are using that solar energy at a rate that far outpaces how fast these fuels can be produced. In the last few decades, we've quite literally burned through millions of years of inherited solar wealth. And we need to switch to using our available solar energy in a much smarter way. The problem is not a lack of renewable resources. Right now, we use about 17 terawatt. And if we look at our combined water, wind, and solar availability, we can see that that far exceeds what it is that we need. And keep in mind that this just takes into account what was considered feasible 10 years ago. So the problem clearly isn't one of supply. We have more than enough. The problem is that wind, water, and solar resources are unevenly distributed, they're variable, and they're intermittent. This means that the real challenge is really one of storage and transportation. We need a way to store solar energy on a seasonal basis and then to move solar energy from places that have abundant resources to places that are lacking. And to do this, we need an energy carrier that is sustainable and recyclable. So this is what we have to choose from as an energy carrier. And there's a lot of elements here, but they're not all well suited for this purpose. So for example, these ones won't react with air or with water. These ones are too heavy. These ones are rare, which means that that fuel would then be expensive. These ones are toxic or will form toxic oxides. These ones are too slow, and these ones are too fast, and so they could be dangerous. And because we need potassium as for fertilizer, and we want to avoid a conflict between our energy system and our food system, then I'll go ahead and take off potassium now. And this is what's left. Now, it shouldn't surprise us that we see carbon here, because carbon is what forms the basis of our energy system now. And while we know we can't keep using carbon fuels, we need to understand what it is that these hydrocarbons offer us. And in short, they're very energy dense, which makes them a really convenient way of moving energy around. The problem is that their oxides, CO and CO2, are released to the atmosphere, and this is what's driving climate change. So what we want is an energy carrier that's also energy dense, but one that produces no greenhouse gases, is safe to store and to transport, and is recyclable. And here we also see hydrogen, and hydrogen is a fuel that doesn't have to produce greenhouse gases. We can make hydrogen by electrolyzing water with clean electricity, and then use that hydrogen in a fuel cell or burn it in air where it only produces water as a byproduct. But when we look at hydrogen from an energy density perspective and we compare it to, say, diesel, we see that it has a much lower energy density, even when it's stored as a cryogenic liquid. And so this means that hydrogen is a great fuel, but it's not necessarily a great energy carrier. One thing we could do is we can stabilize that hydrogen with nitrogen and produce ammonia. But while this does have a higher energy density, it is known to be toxic to the natural world. When we go back to this table, we can look at the remaining elements through a slightly different lens. What if we use these metals to produce hydrogen? In theory, all of these metals will react with water to produce hydrogen. Lithium, however, reacts a little bit too well, and this reaction is very hard to control. So if we want an energy carrier that's also safe, we'll have to keep using lithium in its role in batteries. Iron also reacts with water to produce hydrogen, but hydrogen can be used to reduce aluminum oxide back into iron. Therefore, the reactor conditions would have to be very well calibrated to promote the oxidation route rather than the reduction route. In the AFL, we are looking at iron as an energy carrier, but we're concentrating more on its direct combustion route rather than hydrogen production route. And so these remaining 5 metals are also very high in energy density. So here, when we compare them to diesel, we can see that zinc has about the same energy density, whereas aluminum, magnesium, and silicon have twice the energy density, and boron has 3.5 times the energy density. These metals are also safe to store, safe to transport, and recyclable. So we're looking at all 5 of them, but for today, I'm really just going to concentrate on aluminum, magnesium, and zinc. Of the metal-water reactions, by far the most studied is the aluminum-water reaction. The focus on these aluminum-water reactions has been on enhancing the reaction efficiency through a variety of approaches, but all at low temperatures. And these approaches have all been demonstrated to be effective, but they have drawbacks, which can't be ignored. These drawbacks include increased expense, complexity, and reduced safety because of the lower reaction onset temperature. And besides the safety, the low reaction onset temperature has another drawback, which I'll come back to in a moment. Now, in our group, we're taking a radically different approach in that we're using increased reaction temperature to increase the reaction efficiency. Arrhenius kinetics tells us that the reaction rate will increase exponentially with reaction temperature. And earlier work carried out by our research group has shown this, where if we have a modest increase of just 35 degrees Celsius, we can more than double the peak reaction rate. And we also increase the yield by increasing the temperature. And here yield is represented by the area underneath the curve. Now, metal-water reactions are highly exothermic. The size of these circles here show the relative specific energy of each of the 3 metals, and the divisions show the proportion which is released is heat and that which is released is hydrogen. And in the case of aluminum and magnesium, you can see that approximately half of the energy that's released is released in the form of heat, and then the other half as chemical energy in the form of hydrogen. By increasing the reaction temperature, the heat produces a high quality heat, which can be used directly for power. By contrast, when the reaction is carried out at a lower temperature, that heat of reaction is effectively wasted. So in these experiments, we use temperatures between 200 and 380 degrees, so just above the critical point of water. In each experiment, a measured amount of metal and water were loaded into the reactor, which was sealed, and then heated up to the temperature of interest and then held at that temperature for some predetermined amount of time. Once that time had elapsed, the entire system was cooled back down to room temperature. And the hydrogen yield was calculated by using the difference between the final pressure and the initial pressure. In each case, the amount of water that was loaded into the reactor was there to ensure that there would always be liquid water present, and at the critical temperature that the water would have the critical density. So in our previous experiments using this protocol, we've shown that you can get full yield using very coarse aluminum particles. In this case, we used these 3 millimeter long aluminum slugs and exposed the aluminum to different temperatures of water for 30 minutes. And we can see that once we got to the supercritical regime, we got full conversion. Now, this was with using pure aluminum. So naturally, we wanted to see if we could get similar results using an aluminum alloy. At this point, we had an aluminum can, which we then cut up and put into the reactor with some water. Up until about 350 degrees, as you can see here, there's very little change in the metal. And this also corresponds to a non-existent hydrogen yield. However, once we tipped into the supercritical regime, so once we got to about 380 degrees Celsius, we got full conversion. So our present work is guided by the natural follow-up questions to these previous experiments using pure aluminum. So can we extrapolate these results to other common aluminum alloys? And then we also wanted to explore other metals such as zinc and magnesium. So in this body of work, we set out to test if increasing the reaction temperature would net us the full yield using these other metals. And for each metal, we did a series of tests ranging in temperature from 200 to 380 degrees Celsius. We started with the aluminum alloy. We used two common alloys, 5052 and 6061. We observed that the hydrogen yield increased with temperature in each case. In both cases, we got full yield in the supercritical regime, and we got no reaction at 300 degrees or less. And at 350 degrees, the 6061 produced about 30% of the expected yield, whereas the 5052 produced almost twice that. What's interesting is that the 5052 alloy, the one that with the higher yield at 350 degrees, was cut from a plate with a thickness of about 2 millimeters, which is twice the thickness of the 6061 plate. So just based on the difference between the volume to surface ratio, one would have expected the opposite results. So one factor might be that 5052 aluminum has approximately a 2.5% weight of magnesium, which is a very reactive metal with water, whereas the 6061 only has about half that. And that being said, when we compare the alloy results to a pure aluminum plate with the same thickness, we see that the aluminum plate is more reactive. In fact, with the pure aluminum, we were able to get full yield at 350 degrees. With the zinc, we observed a very similar behavior in that we got full yield in the supercritical regime and then no yield at around 250 degrees. Now, as I mentioned a moment ago, magnesium is very reactive with water, and our results reflect this. We used magnesium slugs, again, about 3 millimeters in length, and we got full hydrogen production at all of the temperatures above 200 degrees Celsius. Now, with the exception of the magnesium, we observed a very similar trend in the efficiency of all the metals tested. Under inert conditions, under ambient conditions, the metals were inert. We got no oxidation below about 250 degrees, and then we got full oxidation in the supercritical regime. So to understand this, we need to look at the changes in liquid water as temperature and pressure increase. Under normal conditions, so up until about 250 degrees, the properties of liquid water are largely unchanged. And then starting at about 250 degrees and going up to the critical point, there are some marked changes in the properties of water. So these changes include changes in the hydrogen bonding network, the dielectric constant, but the key change that we're interested in here is that the ionic product reaches a minimum around 275 degrees Celsius. This means that it has the low ionic product corresponds to a fluid that's high in both H and OH ions. And these OH ions are a more mobile species, which means that they're increasing the rate of hydrolysis, which in turn improves these yields. And we can see that in the results in this region here. Now, as the critical point is approached, the polarity of water shifts and goes from being a non-polar to from a polar to a non-polar. Therefore, the fluid is now capable of dissolving non-polar species, such as metal oxides. At lower temperatures, the mechanism that prevents the full oxidation of these larger particles of metal is the presence or the growth of an oxide layer on the surface of the particle. The presence of this oxide layer can act as a passivation mechanism, which would slow or even prevent full oxidation of the bulk metal beneath. However, in the supercritical regime, these oxides dissolve, or they're at least not coherent enough to actually protect the metal beneath, and therefore exposing new metal to the oxidizing fluid. So, of course, the exception to this is magnesium. And the magnesium is a much more reactive metal. And it's much more reactive than the aluminum and the zinc or even the aluminum alloys. And we saw that the increase in temperature alone was enough to increase the reaction yield. The inert quality of all of these metals under ambient conditions is a built-in safety mechanism. The energy stored in the metal will not be released until the right conditions are created. And these conditions are extremely unlikely to be created accidentally, which means that there's a minimal risk of an accidental or premature oxidation of the metal while it's being transported or stored. Once that energy that's stored is needed, we know that we can get full yield by going into the supercritical regime. We're sure that it's possible to recoup all of that stored energy by creating the right conditions. The non-existent reactivity of these metals under normal conditions mean that they are a safe and reliable way of storing and transporting clean energy. With the exception of magnesium, temperatures of at least 250 degrees were needed to produce any hydrogen at all. But in every case, full oxidation was achieved in the supercritical regime. The increased reaction temperature not only ensures faster rates, but it also ensures complete conversion with the release of both high quality heat, which we can use for power, and chemical energy in the form of hydrogen. And by going to these higher temperatures, we're ensuring that both of these forms of energy are useful. So I'd like to thank you for watching my presentation, and I look forward to answering any questions that you might have during our live sessions. Thank you.